Good morning, everyone. I am very impressed that so many of you woke up this morning and came, because a lot of people have failed. So congratulations to you first. My name is Agnieszka Łukaszczyk. I'm a senior director for European Affairs at Planet. And I'm very, very happy and honored to be moderating this panel on this next generation plenary on small sats involving everyone through their applications. As you know, Planet has a mega constellation of Earth observation satellites, currently the largest one in the world. And I'm extremely happy to hear that there are young professionals, brilliant people that actually are going in the same directions, thinking about the similar applications. And I would like to personally listen to what you have to say, because we might actually kind of use your ideas for planets. Don't quote me on that. Don't tweet that. We don't steal ideas. We have our own. But this plenary is very special for several reasons. One is that there are a lot of plenaries, or several plenaries at the IAC, but there's only one next generation plenary. And what does that mean? That means that we bring people that are younger people and people that have actually had to prove and work very hard to be here. So it's not just that you just get invited. You actually have to go through a very, very competitive process to be selected for this. So these guys are top of the top. And so I would like to give him a big round of applause. So what we're going to do, each of the panelists is going to give a 5-minute presentation, followed by one question. And after that, when everybody finishes, then we can have a proper discussion and debate. You, of course, can submit questions. You know how it works through the Slido. And we are going to address your questions as they come. And ask good questions. Don't be too provocative. No, be provocative. I told these guys that we want to be disruptive. We want to be different and fresh. So you're free to ask complicated questions. These guys can handle it. But without further ado, let's start with our first panelist. Alec Courtwright is a research assistant at Global Science and Technology, Inc., United States. Alec, the stage is yours.
Thank you. Check that clicker. Hello, everyone. So today I'm here representing Destination Space, and I'll tell you a little bit about our mission. So we currently live in a period of rapid development for technology and educational resources. Thanks to online classes and affordable and innovative technology, students have access to a lot of different things and avenues that they can use to enhance their own skills. However, we see that these resources aren't equitably spread to all students. A recent study showed that there's a direct correlation between the opportunities to learn available to a student and that same student's socioeconomic status. Furthermore, we see that opportunities to learn are accountable for 1/3 of the relationship between mathematics proficiency and socioeconomic status. Now, when we compare the resources available to students in agricultural communities to those students in urban communities, we see that there is typically a gap or a disparity with students in agricultural communities usually having access to fewer opportunities. This is especially true in the southeastern United States. So 3 colleagues and I, 2 years ago, decided to found Destination Space on top of our full-time jobs with the mission to help expose students in typically underserved areas to science, technology, and engineering through the lens of aerospace educational opportunities. Now, we try to introduce the students to real science and engineering concepts. We try to provide them with concrete technical skills that they can take into their academic and future careers. And we also work with teachers, education centers, and schools to help train them and worked with our collaborators to provide curriculums that utilize affordable technologies such as these small satellite sensors, which are about this big, no bigger than a Cheez-It or a cracker. And these students can use these sensors to hone their skills and apply the lessons that we teach them. We so far have been able to create 3 different educational programs the first being an introductory small satellite week. Next, we have our year-long after-school program, the ThinSat program. And lastly, we have our Deep Space Cubesat program, which is our most advanced, and it involves students for 2 to 3 years. So all these programs have a very similar structure in that we, one, want to focus on inspiring the students by introducing them to basic scientific and engineering concepts. And two, we introduce them to real-life professionals and teach them concrete skills that they can take into the future. We then connect them with real small satellite aerospace missions. So for example, the ThinSat program, our students build picosatellites, and these teams get to design the payload, the sensors, what research topic they'll address, and then they get to submit a proposal to have their picosatellites launched off of an orbital ATK rocket. Our Deep Space Cubesat mission, we have been lucky enough to have students who have gotten to work with one of the few teams who gets to develop a CubeSat going into deep space, miles space. And they've been lucky enough to actually get some hands-on experience with that. So after 2 years, we know that we're a very young organization. We've only begun to scratch the surface of what can be done for deserving yet often underserved students. But I'm here today to hopefully open up the conversation with all of you experts, to really see what more we can do for these students, and not just in the southeastern United States, but hopefully throughout the world. Thank you.
Thank you very much. Thank you. Well, this is amazing work that you're doing, because we know that it's very important to engage students and give them opportunities so that they get not only interested in space but stick with space, because it's often what we see that you know, young students are fascinated about space, but then actually choose other careers because they don't think there are opportunities there. So in your mind, in your opinion, what do you think the space industry can do actually to attract or to help students, particularly in those countries that are perhaps underrepresented or do not have the same opportunities?
Yeah, so I think to help provide students with more opportunities, the most important thing from what we've seen, students get very, very excited once they realize the opportunities that are available in the aerospace industry as a career, as a research option. So really, the biggest thing I think space agencies or the aerospace industry could do would be to work with teachers and work with schools to help provide translatable information about their accomplishments and their projects.
Yeah.
I think you can't really just throw a technical document at a high school student and say, all right, read it and learn something from this. So we need to work more with the teachers and the education centers to help them develop curriculums so that they can pass on this information. And two, I think it's important to tell schools, tell teachers what the aerospace industry, what skills you think students should have. Because they're listening, they're ready to provide their students with any necessary skills so that they can be ready for the real world and a career, but you just gotta let them know.
Thank you. And actually, we asked the audience, what is the most important skill that students should learn to help them in the potential career in the space industry? And I see computer programming and project management are kind of the top choices there. Would you agree with that?
Yeah, I would agree with that. It also shows me that I need to get a little bit better at computer programming so I can teach the students.
Thank you very much. Thank you. Do we have our, yeah. We're going to move to our next speaker. Are you ready?
Yes, I'm ready.
Very good. So I have Mia. Mia is going to talk to us. Let me just, Mia, I'm sorry. Mia, I lost you. You can take the stage already. Let me figure out the technology here, but something is not working here for me, for whatever reason. But we have Mia, who is, of course, one of our panelists here, and she's a chief project officer at Simera Sense in South Africa.
Yes.
You have a project that you're working on as well, right? And why don't you give us your presentation, and I promise I'm going to be ready with a question for you.
Sounds good.
Thank you.
Can you hear me?
Yes, we can hear you.
Okay. Good morning, everybody. Thank you for being here so early. My name is Mia. I'm from South Africa, a company called Samira Sense. I'm going to tell you a bit today about my passion project and why it is possible that I can do it. So, as we all know, in the past, satellites were custom systems developed by large organizations and government organizations. It was really feasible for small companies to get involved because of the risks that it carried. Immense infrastructure was required, large costs, and lots of resources. It was also difficult for developing nations to get involved and establish the infrastructure necessary for these large satellite operations. It was difficult to justify the costs involved in getting involved in the space race. Of the 54 African countries, only 4 African countries had launched satellites into space by the year 2016. But in 2017, Ghana became the 5th African nation to launch a satellite into space, and Kenya became the 6th. For both these countries, it was possible due to the accessibility of nanosatellites. Small satellites make space more accessible. The development costs are easier and cheaper, and it requires far less infrastructure to develop. Not only developing nations benefited from the small satellite development, the small satellite industry gave the opportunity for commercial development. It gave companies the ability to attain the funding for not only the satellites and their payloads, but also for the infrastructure needed for sustainable development. With the introduction of Cubesats that brought a standard to the standardization to the small satellite industry, industry was able to develop components to the standard form factor that Cubesats brought. That meant that companies could create components to the standard form factor that could be integrated easily with other satellite components for a complete satellite solution. This paved the way for subsystems of satellites to become products for a commercial market. Cubesats were, as we all know, are 10 centimeter cubes, known as 1U satellites. And they grew as satellites were placed on top of each other. These cubes were added together. 5 years ago, the market was dominated by 1 and 2U satellites. Today, it is flooded with 3 to 6U satellites, with larger CubeSat form factors looking very promising in the near future. The launch forecast for small satellites in the next 5 years shows a compound annual growth rate of 13%, with 680 satellites planned to be launched in the year 2022. Half of these satellites are planned to be Earth observation satellites, and that's where we come in. Samira has decided to embrace this opportunity and throw our hats into the small satellite ring. We have grown a very strong knowledge base consulting on large satellite projects in the past for government organizations, and we are now taking the leap and harnessing this legacy knowledge to develop our own satellite payload, aiming to bring more detailed imaging in a smaller satellite. Our goal is to develop a complete satellite payload solution that conforms to the CubeSat form factor. We aim to give you optical ground sampling resolution of 5 meters in low Earth orbit, and we aim to give you imaging in 7 spectral bands using time-delayed integration sensors. We are also working with another South African company called CubeSpace to integrate their stability and control system closely with our CubeSat. No matter how good your camera is, if you shake too much when taking a picture, the picture will be blurry. So we find it vital to match the control and stability system with our payload, and we aim to combine both the payload and the stability system into a 2U volume. In Cape Town, South Africa alone, there are 7 companies building components for small satellite for the commercial market. Small satellites have given the opportunity for commercialization in Africa and given us the opportunity to grab this opportunity that new space has given us. We are also implementing the Space 4.0 principles and smart manufacturing in our laboratories. And we've been able to establish these laboratories due to the accessibility and the ease with which we can develop in new space. Thank you very much.
Thank you very much. So can you give us an example of a potential application of your EO satellite?
Sure. Well, there are many applications. I think I'm going to focus my answer a little bit more on Africa, applications that can be applied to Africa. Earth observation data in Africa is very important for the agriculture, where you can ensure food security and increased food yields. Maritime surveillance is also a very, very handy application. And then, of course, urban expansion and the impact of it, not only for conservation reasons and determining what, like deforestation and so on, but also looking at the demand and supply of energy and water. We have actually just done a proposal for using our hyperspectral sensor to do monitoring of water quality in South Africa. So.
Thank you. Thank you. So tell us, how many African satellites have been launched? Is it 9?
17, actually.
17.
Yes.
22% of you guys either knew or guessed.
No, between South Africa, Nigeria, and Algeria, I think they've launched the most satellites, and it comes up.
Well, it's going to be more, right?
Sorry?
It's going to be more. There's going to be more in the future.
Yes, yeah, definitely. Sure. That's the plan.
Thank you very much. Thank you.
Thank you. Oh.
So I would like to introduce now Ekaterina Timakova. She's a final year student, so you're almost done at the Aerospace Department at Bauma State University, Technical University in Russian Federation. Welcome.
Thank you. Well, sun as a source of life on Earth has always been interesting for humanity. And nowadays, exploring solar activity is a relevant scientific problem which is essential for people around the globe. The sun forms particular space weather that affects not only the work in open space, but also the processes that occur on Earth. And this weather affects the atmosphere and magnetosphere of our planet, causing their changes. And these changes affect the operation of equipment which is sensitive to magnetic field, as well as the biosphere. And the correlation between data on space weather and human health is a very interesting topic for scientific investigation. Space weather forecasting is especially important for manned missions and extravehicular activity planning. We also should consider space weather in the operation of satellites, since it can cause electronic failures in their work and reduce their service life. So it's necessary not only to observe the solar activity to accomplish these critical tasks, but also to find a way to predict the solar events and the space weather, which is a goal of many solar research scientists. And our team works on a group of nanosatellites for continuous X-ray monitoring of the sun. X-radiation emanating from the hot solar gases is absorbed by the Earth's atmosphere, so instruments to detect X-rays should be taken into high altitude. And so, monitoring of solar activity with the help of X-ray spectrophotometers in the range from 0.5 to 15 kiloelectron volts plays an essential role for prediction of space weather. But currently such scientific instruments are installed on board meteorological geostationary satellites or very expensive and unique spacecraft located at the points of libration. Development of such large satellites and launching them into the geostationary orbits and L points is a very long and expensive process. While using the Cubesat and installation of the spectrophotometers on board of them and launching them into low Earth orbit could be a solution for this problem. Using of the Cubesat technology can reduce the overall cost and development. Moreover, we can profoundly increase the redundancy of the whole mission by launching the group of Cubesats with the detectors on board instead of only one big satellite. So currently, we are working on the project of constant observations of the Sun. And our first step is to launch 2 satellites of 1.5U Cubesat format, so as one of them is always on the illuminated half of the orbit and can monitor the Sun. The feature of our satellites is using the rotary two-blade solar sail. This technology is rather simple, cheap, and doesn't require any propellant. Moreover, we can use the sail for deorbiting the satellites at the end of their lifespan, so they won't become the increasing space debris. It also allows much faster deployment than passive phase separation using drag forces. And in conclusion, I'd like to say that this concept was developed by students and PhDs of Bauman Moscow State Technical University. We all are members of the Youth Space Center, which is an organization of our university supporting and encouraging young space enthusiasts. And we all truly believe that the developed concept will be useful for all of us. Thank you.
Thank you very much. The question that I have for you, and it's also the question we've asked the audience, but I'm wondering what your opinion is, because this is also important for companies like Planet. What do you think, what can we do to ensure long-term sustainability of mega constellations? Because this is a big question, right?
Yes, that's a very interesting question. Thank you for it. Actually, as far as we have the solar sail unit on board our satellites, we can use it exactly for this purpose. So as in low Earth orbit, the atmospheric impact prevails over the solar pressure, the solar sail acts mostly as a drag sail. And while deploying it from the board of satellites, we increase the middle section of them and increase the drag area. And so we can control the constellation with the help of it, like closing and unfolding it. At the certain time steps, we can keep the angular distance between the satellites sustainable. And so it's like a passive maneuver device for our satellites.
Very, very good idea. I'm taking notes. Thank you very much.
Thank you.
So our next speaker is the CEO of Spectral from France, David Henry.
Thank you. So good morning, everyone. Thanks for waking up that early. So Spectral is a startup. We are designing operation and electric propulsion solutions for the small satellite market. So we are essentially building these small thrusters for the small satellites. And the idea is for me today to introduce how I think that electric propulsion can change the small satellite market. So today, constellation owners essentially launch their satellites. They have 2 ways of launching their satellites. The first one is with rideshare or piggyback, where some small satellites are being launched with a larger spacecraft, and everything is sort of going at the same orbital position. So for me, this is a bit the equivalent of a bus. It's fairly, and I insist on the fairly, cheap, but everyone is going in the same orbit. Now, on the other hand, you have dedicated launchers. So right now, they are not mature, but hopefully they will be, and then the constellation owners will gain flexibility, because dedicated launchers can go to a certain extent where you want to go. But it's more expensive to launch a satellite on a small rocket. And for me, it's a bit the equivalent of a taxi. So essentially, you have to compromise between cost and flexibility. And what electric propulsion does is that you can divide the launch orbit and the operational orbit. So now they become 2 distinct orbits, and it means that you can optimize both. So on one hand, you can optimize the launch orbits. For instance, use the rideshare, reduce your launch costs, but then go where you want to go. So you have the advantage of cost and flexibility. But you can also optimize your operational orbit. So that means essentially that you can go further away from the Earth, for instance, in order to gain coverage, which is useful for internet or Internet of Things applications or tracking AIS. You can also move closer from the Earth to increase your picture resolution for Earth observation application, for instance. You can also downlink more data because you are closer from your ground stations. And finally, you can mitigate space debris and space pollution. As we've seen before, deorbitation is important, and with electric propulsion, you can safely re-enter into the atmosphere. Well, safely you burn into the atmosphere, but at least you do not generate debris, and you can also avoid collisions. But to do that, you need 4 small satellites to have both a high impulse, because you want to pack a lot of energy in a constrained volume, in order to give a large range to your small spacecraft. But you also need a high thrust, because, as I said, electric propulsion is used to go from your launch orbit to the operational orbit. Now, this maneuver can take some time, and it's time that you lose because you do not generate revenues during that period of time. So you want to make that period of time as short as possible. So that's what we are doing at ExoTrail. Essentially, we are adapting the technology that is used on the majority of large satellites, which is the Hall effect technology, that has both the advantage of having a high impulse density, but also a high thrust. So compared to other solutions for larger satellites, we are much smaller, much cheaper, and we consume less power. And compared to solutions developed specifically for small satellites, we are more efficient. It means that we have a higher thrust. So to conclude a bit for us, our mission statement at ExoTrail is to bring agility to spacecraft. It's not to deliver propulsion to spacecraft. For us, propulsion is the mean, it's the first way. That's why we've raised money and we are employing a lot of people. But in the longer term, we do believe that there will be other ways to provide this agility. And we are strong believers of what's called on-orbit servicing. So on-orbit servicing is essentially the capability to act with a satellite after it has been launched through inspection, patrolling, repair, repositioning, and later on manufacturing and assembly. And for all of this, you need, for nearly all of this, you need some maneuvering capability, so electric propulsion, but also operation and proximity operation technologies. And it's to prepare the future and to prepare this future that we are right now developing these technologies at ExoTrail. Thank you very much for your attention.
Thank you. Thank you. It's very interesting what you're working on, because we can safely assume that on-orbit servicing is going to be the future, the way to go. But do you think we're going to reach anytime soon a point where it's going to be actually economically sustainable?
So I think there are really two questions and two ways to see it. Is when will it be technically viable, and when will it be economically viable? So to give you an idea, the first on-orbit servicing vehicle that will be launched by Orbital ATK in the US, and actually early next year. And this vehicle will already be capable of attaching to a satellite and reposition it in orbit. So technically, I think it's much closer than we think. Mm-hmm. Now, it doesn't mean that it will be economically viable. And the thing is, it doesn't only need to work for it to be economically viable. It needs to work really well with an extremely safe approach. Because when you start to move things around in geo, you don't really want to crash a satellite, right? So it needs to be really safe first, so that's on the technical point. And you need to, basically, because it's quite expensive and complex, you need to find use cases where it adds, for me, a real disruptive value. And that's why I'm believing more in manufacturing and manufacturing things in space and assembling things in space. And for that, I think the business case is not yet promising. So I would say that the good sort of timeline is probably 2025 for it to be compelling in terms of a business case, but probably not before.
Okay, well, let's see. So it seems like our audience thinks that we're going to launch a lot of satellites in the next 5 years, right? So either over 1,500 or definitely over 500. Do you agree? Do you think that's?
I'd say it's the good order of magnitude is probably 1,500. Yes.
Yeah.
Of course, I hope more, but it's also important to be, let's say, careful with estimations that say that we are going to launch 10,000 satellites in the next 5 years. So yes, I would agree with these figures. Yeah.
Thank you. Well, I would like to say though that when we launch these satellites, let's be responsible space actors and not cause debris, and think about sustainability not just of those satellites but of the space environment as a whole. Because I think that's important. Thank you very much.
Thank you.
My next speaker is Marco Gomez. He's a research engineer for the Costa Rica Institute of Technology. Welcome.
Good morning. So my experience focuses on developing the first satellite project in a non-spacefaring nation. I will give an overview of the mission along with lessons learned that could be applied to other countries wishing to develop their first satellite. Over the last 3 years, I had been working as project manager of IRASU, a project consisting of designing, developing, launching, and operating the first satellite in Costa Rica and Central America. It is a joint initiative between the Costa Rica Institute of Technology and the Central American Association for Aeronautics and Space. IRASU has two main objectives. The first one is to develop capabilities related to space technology in a non-spacefaring nation. This means training the next generation space scientists and engineers in the country, but also developing a strong infrastructure of key players in academia, government, and industry. So IRASU will be the first of many space projects in Costa Rica. The second one has to do with the scientific component, the scientific mission. We wanted to develop a project that would display immediate benefits of space technology to the country. That's why we decided to monitor carbon fixation in Costa Rica's rainforest and support the country's overall goal of becoming a carbon neutral entity by 2021. The mission is divided into 3 segments. The first one is the remote station. As its name suggests, it's located in a remote location that is difficult to access by researchers wishing to acquire data. The remote station consists of a series of sensors called dendrometers that are measuring tree diameter growth, along with a weather station and an autonomous communication station, which collects all the data and transmits the data to the flight segment once the satellite is in the line of sight. Flight segment consists of a 1-unit Cubesat, which acts as a store and forward system. This means that it collects the data, stores it in its internal memory, and then forwards it to the ground segment once it receives the command. The ground segment consists of a communication station, mission operations, and a data visualization center, where we're analyzing the data, both of the dendrometers and the satellite, to publish it in a visually appealing fashion in order to generate more interest in science and technology in Costa Rica. The satellite was launched on April 2nd of this year from Cape Canaveral on board a SpaceX Falcon 9 rocket, headed toward the International Space Station. It was then deployed on May 11th from JAXA's KiboCube module when it started operations. Over the first months of operations, we have successfully demonstrated store and forward capabilities, transmitting data from the remote location to the ground segment on an almost daily basis. The dendrometers have also proven to work as designed, acquiring daily biomass data and tree trunk growth. One common problem when developing a space project in a non-spacefaring nation is the funding. It's always important to remember that government funding is not the only option. One can also implement innovative strategies such as crowdfunding, using a platform like Kickstarter, which will not only allow you to secure the funds, but also will allow you to give media exposure to your project, and therefore gain more support from civil society. Another strategy would be to secure sponsorships from private entities that align with the vision of the project. Both of these strategies were implemented in IRASU successfully. One of the key aspects to success of this project was the strong infrastructure of national and international partners. For example, Our partners at the Kyushu Institute of Technology allowed us to overcome two of our main obstacles: testing of the satellite, which was done at QTech's laboratories in Japan, and the launching of the satellite, which was deployed from JAXA's KiboCube module. An important thing to understand about Irasu is that it is a proof of concept. We wanted to demonstrate a platform to monitor environmental variables, but we want to keep expanding it. Through international collaboration, we believe that we can have more satellites in space and remote stations all around the world to build a platform that is robust enough to monitor climate change for many years. Thank you.
Thank you, Marco. So it is, we hear a lot, a lot of countries want to have their own satellite. And so what would be the advice you would give to them when they want to start building and launching their own satellites?
Good question. I would say that the main advice I would give them is to show how space could benefit their country. So, for example, in Irasu, at first, we were thinking about it as the first satellite in Costa Rica and Central America. And this way, we would gain the funds necessary to advance the project. But it was until we started talking about its application, about supporting the country's goal of becoming a carbon neutral entity, that people really started to get behind it and support it. So my main advice would be that to show the people of your country how space technology could benefit it.
Yeah, I think that's how it starts, right? There has to be awareness of the usefulness of these satellites, yeah. But please, we are dying to know, so which country is not using the Cubesat standard?
It was actually a trick question.
It is a trick question. I have no idea, by the way. I just guessed, and I'm not going to tell you what I said if it's wrong.
But it is South Africa. In 1999, they launched their first satellite, and it was a 64-kilogram satellite. So they didn't use the Cubesat standard.
Ah, Mia, did you know that? Thank you very much. Thank you.
Thank you.
So last but not least, speaker Anastasia Volkova is an astronautical engineer at the University of Sydney, Australia.
And as of recently, I graduated PhD from Aeronautical Engineering at University of Sydney. So now I can be speaking to you as the founder and CEO of Fluorosat. And I want to tell you about the revolution that's happening in aerospace that you are aware of, but you might be not thinking that you are a part of. It's a revolution in agriculture. Agricultural fields are the ones that they're benefiting the most out of the Earth observation missions we've heard about, out of the monitoring missions and environmental applications. And this is something that I realized halfway through my PhD. I realized that my research had an application. And I thought, okay, well, I must then go and implement it because, as a serious person, you go and own the problem. So I started Fluorosat, and under 2 years ago, that was. Now we are 15 people looking after crops on 3 continents. And I want to tell you how precision agriculture is developing and why aerospace is so crucial for it, including small satellites. Precision agriculture. Okay, most of you, I'm assuming, are aerospace engineers here. Can you please raise your hands and show me who are the aerospace engineers here? Yes, my crowd. All right, so I need to explain to you the way I explained to myself 2 years ago what is precision agriculture. And I hope you won't judge my aeronautical explanation of it, those environmental people in the audience. So precision agriculture is when you're trying to solve a problem to feed in more people with less arable land by doing things more precisely, meaning that if you know that there is a section of your field where you need to apply more fertilizer, you don't apply the flat rate all the same amount everywhere. You apply it in a very distinct point, and you should know the amount of fertilizer you want to apply. Well, the concept is interesting, but the implementation is even better because it includes some of the amazing toys that we love to play with, right? So first is, okay, GPS-driven tractors. This is something from agricultural industry. We will look into why that is an important component out of 3. Also, the favorite part, Earth observation satellites. Those constellations of Landsat, Sentinel, and new spaceborne missions on Cubesats, how are they contributing to precision agriculture? And most important point that is not often raised, but that I'm trying to advocate for, is that these two components are simply not enough to make precision agriculture work. What makes it work is when you implement decision support, when you include the software that can ingest all of that imagery, that is more and more of it every day, and can actually inform decisions in the field. Well, I'd like to then dive into both of these into all of these three factors and tell you why they're essential. So, GPS-driven tractors. For us, we are used to cool technology, and we think aerospace is the coolest, right? Also, there are other industries that have amazing things that benefited from aerospace technology, like GPS-driven tractor. Almost every tractor is now able to be equipped with the GPS-driven steering module, so it's completely autonomous. And the importance of that is that it knows where it is at any given point in time, so you can program it to do what you want, and you can sip coffee, maybe out of the cabin, maybe on your couch. Now here, this is a very important part. It needs to know what to do where you send it to those locations that are indicated as locations of interest. How do we get information to really know where the tractor should go? This is not a trivial situation. In Australia, where Fluorosat is based, fields are of the size of a small European country. So you cannot walk around and find out where the tractor needs to be. Instead, satellites solve this problem. They take images in infrared spectrum, and if you want to have a takeaway from today's presentation, this is something maybe new for you. In infrared, the stress of crops is visible before it's visible to human eye. That's why the satellites are so important. Beyond visual range, the stress is earlier detected and mitigatable, of course. So we're collecting all this imagery, we are pouring it down somewhere, and let's hope that there is software to crunch through all of this, not just to show images, but as I said, to inform decisions. Well, this is a nice vision, but in reality, there is hardly ever any software that does that en masse right now, and instead, we have a human factor. The human factor meaning that the agronomist in the field is supposed to look through all of these images. And if I'm looking after 10 farmers, they have each 50 fields. How many images do I have to look at every 3 days when Sentinel comes over? Masses. This is not something that an agricultural professional can do. They have no time for this. And this is how we get, we saturate their attention. They are not capable to take any more of this imagery, and then they are not capable of making the decisions that we need them to feed us, including our aerospace community. So what needs to happen there? We need to remove the person from this, waterfall of images and actually put a smart system there, the piece of software that really does it. The solution that we developed is called Fluorosense. It's an online decision support platform, and what we do with it, we enable the users to teach their own machine learning model so they can mark up the imagery, show exactly where the tractor needs to go, and the model adjusts the recommendations to their own field. And I hope today you didn't just learn about precision agriculture, but also why it is an industry involving everyone. Thank you.
Thank you very much. We can clearly see that you're extremely passionate about the work that you're doing, which is great to see, because I think out of passion, great results come. So that's very good to see. But could you tell me do you see the push from a publicly owned to privately owned market when it comes to space industry, and I'm thinking about startups or large and small companies like reflected in agriculture. How does that affect the technology development and adoption?
Yes, certainly. There's a lot of new players in new space, people launching new satellites. We want all of these satellites to be successful with all of the different pieces of technology, because honestly, with the smallest satellites, you can have a smaller sensor, you can iterate on it very fast, and this is the edge which agriculture is getting, because simply the stable constellation gives you the certainty that Landsat and Sentinel will be there. But even for them, the mission takes, as you know, years to develop. And instead, these guys and some of you in the audience, you can launch a small satellite and you can improve on the sensor every year. This is vital because we have better sensors on Earth than we are capable of quickly putting into space.
Yeah. Yeah, that's very true. That's very true. That's what we call agile space, right? It's much faster. So how many spectral bands does a typical hyperspectral image have? What's the right answer?
This is what I wanted to demystify for you today. When you hear hyperspectral imagers, they typically have much more than 6. We think hyperspectral is 16, 40, 64. So if you think of an imager that has only 6 bands, that's called multispectral. So that's just a takeaway for you all.
Thank you.
Thank you.
Thank you for your presentations. Let's have a bit of a discussion. I know you asked how many people are engineers, aeronautical engineers in the room, and it seems like there are a lot. But we also want to, I always tell people that you don't need to, and I really do often, that you don't need to be a rocket scientist to work in space. That actually there's room for involving everyone, right? We can involve everyone in the space sector. We need lawyers, we need economists, we need physicists, we need people that are good at policy. Do you guys think that's true? That's number one. And how do we attract people from different sectors and from different interests to actually come and be involved in the space sector? Yeah?
I actually had a discussion with somebody yesterday about this topic, and he was telling me how important it is. Us engineers, we think very technical, and this is the way we're going to do it. This is the way we're going to solve it. And especially, with the heritage of previous missions, you try and solve the problems as you did in the past. And how important it is to put somebody completely out of the field into those meetings and into those discussions, just to bring a different perspective, a different edge into the design, and ask the questions. But why? Yeah. Why are we doing it this way? Isn't there a simpler way? And I think that is very important.
Yeah. And I think also, having an idea and building a satellite or building a software is one thing, but then you need to have people who actually know how to sell it, who know how to actually introduce it into the market, so we need all kinds of different skill sets. For instance, I'm not an engineer, and I admit I'm not an engineer, but I've been working in the space sector for 12 years, and I find it that there is room for really everyone. But let's talk about small sats a little bit more. So do you guys think that there is a trend that obviously we're going to see more small sats, but is that a trend that actually the small sats are going to replace the big satellites? Do we still need big satellites? Can small sats do everything that the big satellites are doing, or are they more complementary? We need both. Or do you think that there's a shift and a change for small satellites? So in maybe 10, 15 years, all we're going to see are going to be small sats. What are some thoughts? David, you're looking at me, so I see you have thoughts.
Yeah, I think it's going to remain complementary. I think some capabilities of large satellites today can be replaced. You see in the US, for instance, you have a lot of questions of replacing some governmental military spacecraft by more small satellites to increase resilience. But for some areas, you will need large satellites because you would need power, you will need very high resolution. Today, we are far from being able to, maybe not far, but we are not to the point where you can reliably send small satellites in geostationary orbit, and there is still a lot of things that you can do only in geostationary orbit. So I think it's going to be complementary, and basically where you need really performance in terms of resolution, I would say that you will still need larger spacecrafts, but when you need coverage in the broader sense, the coverage revisit rate, when you need numbers, then you will be more efficient with small satellites. But I think they will remain complementary.
Yeah,
I think.
I would like to agree with what David said. I mean, we can't change the laws of physics. So to see high resolution, you do need bigger satellites.
Yeah.
And I think, so I agree with you, more complementary, where you'll get a higher temporal resolution with smaller satellites like Planet does. But then if you need those high resolution images, you'll go to the bigger satellites.
No, that's true. And this is actually what we're saying, because sometimes I feel like there's this bit of a competition between what we call new space and traditional space, and it seems like you have to choose one or the other, but there's actually room for everyone, and we can work together, and I think we can achieve a lot more working together rather than competing, right? So that's very true. Ekaterina, I think I have a question for you about cells on CubeSats. Cells on CubeSats, they are useful, but why do we have to rotate them?
Well, you mean the standard?
Yes.
Yes. Well, as far as it's really easy now to produce the CubeSat following the standard which is already exists, and there are many already existing transport launchers, yes, transport containers, and so for students, I guess, it's the best way to produce CubeSat following the standard, and it is very comfortable to locate all these onboard systems inside of it, and also like make several of them together, yes, like similar ones, and then launch it, and then make the constellation. So I guess the size of CubeSat is like it's different one, yes. So it's can be of several sizes, and we can. Yes, I just think we should follow it.
Thank you.
Yes.
Thank you.
Probably next time we will start producing spherical.
Yeah. Well, that leads me to the next question, because somebody asked a very interesting question. If you were going to be on this panel, or if you knew the people who were going to be on this same panel, small sats next gen, well, then it wouldn't be you, and 20 years later you will not be the next gen, but the next gen 20 years from now, and they will be talking about small satellites. What do you think they're going to be talking about? Where do you think we're going to be 20 years from now?
Yeah, definitely it will be the topic of space debris, because it's more accessible space right now, and I think it will be even more accessible in a few years. So there will be more satellites launched, more debris in space. And another one I was thinking about was how to manage the communications band due to saturation. Because if you have more satellites in space, you have more satellites needing to communicate with Earth. So I think that will be a big issue in the future.
Yeah.
I'm totally on board with the space exploration. So there was a question on how much it costs to launch a CubeSat to Mars. I don't know how much it costs, but I would say that in 20 years from now, I want the next generation panel to tell us what they're doing with the Martian CubeSats, and how are they growing potatoes there, and how are they looking at them, and how it's possible through Martian atmosphere.
Go big or go home, right?
Yes.
So, excellent. And actually, I wanted to ask you another question. I mean, agriculture obviously is huge when it comes, a huge customer of Earth observation for Planet. Actually, this is our biggest sector right now, and this is something that is going to continue, and it's going to grow. Is it difficult, do you think, to convince agricultural companies or farmers to use satellite technology, because they have so much other options as well? Is there an added value? What's the added value? What's the selling point?
Yeah, it's an excellent question. And our belief is that you should not give an extra ball to juggle to a busy man. So that was kind of the part of the vision that I presented, and we want to abstract as much of the thinking out of it as possible. The similar way as the Planet distills it to analytics and delivers you the information in numbers, the agriculture is even easier. It's the is a data-driven business, and convincing farmers is not really a good arena to play in. You should really go to a crop advisor, because they are an educated person who is using the software, who's using the mapping, and they've been using satellite imagery since the first image of Landsat, I think.
Yeah.
So yeah, they've been on board always.
Yeah, but that's the thing. I think the end user, so be it a farmer, they want a solution. They don't really care where the data comes from, right? They want something that works and that is easy to use. And so it's in our interest actually to provide them with application or solution that is actually useful, right?
Yes, whether you fly drone, plane, satellites, whether you do some other black magic, they just want to know what they need to do tomorrow morning at 5 a.m. So.
Exactly.
Yeah.
Exactly. So Alec, I'm wondering, do you think we're going to have more interest in space in the future? I mean, for young people, what do we, I mean, like I said, it's a passionate topic. A lot of people are interested. What do we do to actually to make sure that they stick with the sector and actually contribute to the sector and work for the sector? Like, what do we need to do? I mean, education is one thing, right?
Yeah.
But is there anything else? Do we assure jobs, internships? How do we keep them in?
Yeah, I mean, I would say opportunities and internships are critical. I mean, it's such an exciting time, I think, with all of the new players coming into aerospace industry, all of the new innovations. I think many students are already kind of thinking that route for aerospace as a career, but many of them just don't know what steps to take next. So I think providing opportunities and internships is going to be critical. I think one thing that we've seen in our experience with students is that really many of them, it's rarely, if ever, pretty much never, an issue of capability. I mean, all of our students have done some really amazing things. It's just building their confidence and giving them the correct structure and guidance at the beginning so that they can apply those skills. We've had students who, even in just doing everyday tasks, counting screws on a 3D model, just having that real hands-on experience was enough to give them the push to go into aerospace.
Sure. And I agree. I think internships are key. I actually didn't think about space or studied space at the beginning. And I got an internship at the Space Generation Advisory Council, thinking that it was going to be cool just to have an internship in Vienna. And then I got completely brainwashed in a very positive sense. And actually, I wasn't even, like I said, space sector wasn't a plan for me, it wasn't a goal for me. And 12 years later, I'm still here. I'm totally converted and preaching the message. So I think that's how you get an experience. Is how you get attracted is through an experience, a positive experience. So I agree. We are going to have to wrap it up. I know we're just kind of starting the interesting conversation, so we can take it offline. But any last words you would like to leave the audience with? Keep it to 30 seconds. Alec, go.
Yeah, I think just reach out to schools, reach out to teachers, and let them know what skills you all are looking for in students in the future generation.
Thank you. Mia.
I would just like to say new space or small satellites are creating fantastic possibilities, and we should really just go for it and try new things and help humanity out from space.
Yep.
I'm personally thinking that if you have already started being in space, it's just impossible to stop. And yes, it's small satellites. It's a very nice launch pad for getting higher.
I know it's really, if you are in the young generation, is well, we are really lucky to be here, but is to try and go ahead and try things and never not do something because you think you can't do it. Sometimes you won't be able to do it, but it's okay, and you'll do something else. And the only way to find out if you can is to try. So it's really to try around, and I would say that, yeah.
I was going to say something very similar to David. But basically, it's a great time to be in astronautics. The community is growing, the industry is growing, so don't be afraid to try and go for it.
And I would urge you to collaborate. I would urge industry collaborate with startups, engineers collaborate with scientists, and make better applications out of what we have in aerospace technology.
Yeah, very good. Very good. So I would like to conclude by saying a couple of things. One is that I think we have gone very far in the space sector when it comes to involving everyone. When I started coming to these events, and you've always heard this kind of notion that space, and I hope I'm not offending anyone, but it was a old boys club. And today we're here, and 50%, I heard almost 50% of attendees for the IAC are below 35, which is incredible. It's amazing. And we have this also gender diversity. We see a lot of strong women. We have people from literally every continent. And this is something that I hope it will continue. and you guys are contributing to that, and you're a true talent, and I'm very, very happy to hear that young people like you are interested in small satellites and are really trying to make a difference. So thank you very much. Enjoy the rest of the IAC, and I'm sure you will get a lot of questions from the audience offline, but thank you very much.
Thank you.
Thank you.